In lab, you guys had a chance to see resonance. Now, resonance occurred when a small application of energy could cause more things to vibrate and their amplitudes to get bigger. So you saw it happen on the washers hanging from the fishing line, and you saw it happen with the mass hanging on a spring, and you were able to find the natural frequency of the system. Now, natural frequency refers to, in objects or systems, frequency at which it vibrates when it's struck. So it'll oscillate at its own natural frequency. And most objects have a natural frequency. Some are specifically designed not to. Bridges, they don't want to have a natural frequency because if a bridge starts to oscillate at its natural frequency, it could shake itself apart. Um, but once an object is struck, it will continue to oscillate at its natural frequency without the addition of energy or an application of an external force. And a system doesn't necessarily have only one natural frequency. In fact, musical instruments have multiple natural frequencies. That's why we can get multiple notes out of the same instrument. So a vibrating string, which we'll look at in our next unit, has a fundamental frequency, and then it's got several higher frequencies that it can also play. And a column of air has a fundamental frequency and several higher frequencies that it can also vibrate at. Now, a pendulum has only one natural frequency, and it's given by F equals 1 over 2 pi times the square root of G over L. An oscillating spring, or mass on oscillating on a spring, also has only one natural frequency, and of course it's 1 over 2 pi times the square root of K over M. Now, you guys did the lab where you actually found the natural frequency and measured the natural frequency, and they were a little bit different. And chances are it's because of the M. We were considering only the mass on the end of the spring to be vibrating. But in reality, when that spring stretches and compresses, some part of that spring is also vibrating as well, which gives it a little bit more mass, which tends to make our frequency a little bit smaller than our ideal or our calculated. And that's okay. What happens is you have to consider about a third of the spring to be vibrating. So if you add a third of the mass of the spring to the mass of the vibrating object, you'll probably get an answer mathematically that matches what you measured. Now, an external force can be applied that makes the system vibrate at a frequency other than its natural frequency. Generally, we're not too worried about that. We are worried more about resonance. Now, resonance occurs when energy is added to a system at its natural frequency. And so if I have the two tuning forks and I hit one, another one that's tuned to the same frequency is going to start vibrating because energy is transferring to it, and the little bit of energy that the air carries to that tuning fork always comes in phase with the system. So it's always adding energy at exactly the right moment. And when you add energy at exactly the right moment, the vibrations become large in amplitude. And so that's why you could see when the washers were swinging back and forth, if you swung one and the one that had the same length, it started swinging and they progressively got bigger because the energy was being added and transmitted through the string at exactly the right times so that the two helped each other out. Pushing a child on a swing is an example of resonance. You push right when they're at the top of the swing, so that you are adding them to, so that you're giving energy to them at the right time, so that you're helping yourself, not hurting yourself. So small forces at the right moment drive the swing to enter greater heights.